In this part of the AlphaZero for Connect 4 series, we'll be continuing on with our neural network building. So in the last video, we went through and initialized all of our layers, created our Connect 4 model class, and initialized all the layers that we'll be using in the network to start. We also talked about just how this fits in, why this architecture makes sense, and how it fits into the bigger picture of the AlphaZero algorithm. So again, this is kind of the decision-making module and kind of the brain behind the whole algorithm itself, what is actually deciding which piece goes into which column of the board. So we'll move on here. As I mentioned, we've already defined all the layers we'll be using. Now we just need to define how we're going to connect those layers up in a single forward pass of the algorithm. Or in other words, how does a single state of the board get from the start, from the first convolutional layer, all the way down to the policy and value heads of the network. So one thing we forgot to add in the last portion of the series is we just need to, at the end of our init method here, we're just going to call self.to and pass that device parameter. So this is just telling PyTorch we're going to pass it to this device here, which will be, in our case, the GPU, but whatever device you'll be using to actually train the network itself. So the first thing we'll want to do in our forward pass here is reshape the data. So our data, we're going to expect X to be in shape as we've discussed 3 by 6 by 7. This is 3 channels, 6 rows, and 7 columns. But we actually want to, when we train the network, we don't want to just pass one board for each training iteration. We want to actually pass the data in batches, because we'll have thousands of these training points, and we want to, it's very common to pass data through the network and train in batches. So we'll actually want to be adding a dimension for our batch size. So we can add dimension. And the way we do this in PyTorch is just x.view, -1, and then 3, 6, 7. So I'm not sure why exactly this is called view in PyTorch, but this is basically the torch equivalent of NumPy, the reshape function in NumPy. So we're basically just adding that. -1 means we're not actually specifying the batch size yet, but we're just adding, we're going to have some sort of extra dimension here at the beginning. And the reason we're not specifying that just yet is because that will likely be a hyperparameter that we'll be tuning throughout the training process. So we don't want to hard code that into our forward function. But now that we have our data in the right shape, we can actually start passing it through the layers of the network. So the first one, obviously, is this initial convolutional layer. So we can start by calling that initial conv, and we can pass x. And then we'll also just, in the same line here, pass this through our initial batch norm layer. So this will be our output here. So now we've gone through our first 2 layers of the network here. And then we'll also need an activation function. So basically, after every one of our convolutions, whether that's in our res blocks or in this initial convolution, we'll pass it through a rectified linear unit activation function, which can be called from this functional library here. So this is just f.relu, and this is definitely by far the most common activation function used in deep learning. So we will be just calling that after each of those convolutional layers. So we've now defined how it will be passed through, or how x will be passed through these first 2 layers. Now we can move on to our ResNet blocks. So before we get into the code for the ResNet blocks, I want to just pop up a quick visualization of what the ResNet actually is. So there's this website called tensorspace.org. They basically have just kind of crude visualizations of some of the common neural network frameworks that have been used or have been found to be useful in the past. So this is a ResNet 50 here, which basically just means it has 50 of those blocks that we're creating. And this is, I believe, the one that made its breakthrough on ImageNet back in 2015. But yeah, it's not a super, I guess, useful visualization other than just to kind of show you the connections between the layers. So each of these are convolutional layers, and we can kind of zoom in on one of them here. So the purpose of this visualization is to show the shapes of each of the layers. In our case, these are all the same shapes. Every convolutional layer will start with the same shape data. And then also the colors here, you'll see if you see that connection going between the two layers here are how the data is being fed from layer to layer. So on all of the yellow ones, you'll see the data goes straight to the next layer and so on. But from all these red blocks, these are your basically skipped connections is kind of the breakthrough that ResNet made. I'm actually not even super familiar with the theory behind why ResNet works as well as it does. I know it has something to do with solving the vanishing gradient problem, but basically the innovation here was by passing the data not only from the convolution, straight through all the convolutional layers, but also passing the same data to the following layer afterwards. So you see this red layer here is connected to both the next the next two preceding layers. So yeah, this visualization here is can basically just give you an idea of what this network looks like after we define all the layers. But anyway, we can get back to actually coding this up. So how that works in practice, we're still going to take our x, and the first thing we're going to do is we're just going to make a copy of it. So we'll call this res, and this is basically a copy of x that so we'll pass x to the next layer, and we'll pass res to the following layer after that. And this is why we actually have two convolutions in each of the res blocks, so that we can pass one to conv1 and one to conv2. So the way that works, we can kind of copy from our last layer here. We want to take our first convolution, or I suppose we should be coming from res block 1, and batch norm 1, and we're going to pass x. And the way this works in practice is we need our activation function. I'm actually just going to move the activation functions on the same line to kind of keep things tidy. So we will add our activation after our convolutional block, and then we'll move on to our next convolutional layer. So we'll have the same structure here, except this will just be batch norm 2 and convolution 2. And then here, basically all we need to do now is just add that x that we made a copy of, just add it to our resulting x. And so this is really the innovation of these ResNets. We basically just have this sort of, residual piece of information being added at the end. So this is basically our res block 1. So we'll call this, just make a comment here, res block 1. And we'll also need an activation function after we make that addition as well. So let's just create another rel_u here. And this whole piece will be what we'll call our res block. So now to basically pass the output of this block to block 2. And again, as I mentioned in the last video, this can be done in a much more dynamic way, or I guess like a programmatic way. But I think this is kind of simpler to visualize for now. And since we're just starting with 2 of these blocks, I think it's easy enough to just give them different names outright. So we'll call this res2. So then we have our res blocks there. So the last thing we need to do before we can kind of look at the summary of the network we created is we need to pass it through both of these heads of the network separately. So this is kind of the innovation between AlphaGo and AlphaGo 0, or one of the innovations. So in this paper that we've been kind of recreating, and actually in the algorithm that they used when they actually played the Go champion, Lee Sedol, they didn't have these networks as, they didn't have two heads in the same network. They had a policy network and a value network. And one of the innovations they made between AlphaGo and AlphaGo 0, AlphaGo 0 was much better than than the original version, by the way. One of the innovations they made was by combining these into the same neural network. And kind of the thought process behind that, or the intuition there, is that the network needs to distill the same information either way, whether it's making a value judgment about the board or it's predicting the next action. The distilled information is still the same. So by having the gradients flow through both of these heads, both the value head and the policy head, you're actually, first of all, saying two different things about the board, right? The value of the board state is not necessarily, or it is different than the policy information. So you're giving it two loss functions instead of one, but you're also capitalizing on the fact that this distilled information that the network needs to learn about the game is actually the same, right? Somebody that understands Connect 4 at a very high level can both make a value judgment and a policy judgment at the same time using the same information. So I think that was a very cool innovation here, and the way we actually implement this in practice is just by basically now passing this x through to, so we'll call this value head and policy head, and we just want to pass it through each of these layers. So starting with the value, we can pass it through value conv, we'll pass it through the batch norm, and again rectified linear unit, and then we'll pass it straight through to this fully connected layer. So we have self dot. Also, whenever we transition from this convolutional bit to a fully connected layer, we will have to reshape the data again before. So yeah, so basically, I guess we can write this first, but we can pass it through this fully connected layer, and then also straight through to the value head. And we'll put not self, but f.relu on each of those, or on this one at least. And we can reshape here in the same way. -1, 3, 6, 7. Except this time we only want to add, so we want to reshape this into basically just our one batch dimension and the number of, I guess, the number of inputs to this dense layer. So the number of inputs is going to be exactly, one input for each output of the previous layer. And we are, at this point, remember, back to our 3 by 6 by 7 shape here. So the shapes are kind of something, by the way, that you have to tinker with a little bit and really think through to get them right. To basically, you figure out which layers you want in your network, and then you can pass data through them and see what the output is, or you can go through the calculations yourself and actually figure out how to assign these. It's not something that you just come up with on the fly like I am now. These are something, these are values that I carefully thought through in defining or in building this network in the first place. So this is kind of the intuition behind it, but yeah, you will have to, in building a different network, kind of do some tinkering and experimentation to really get all these shapes nailed down correctly. But anyway, and then the last thing on the value head is we want to, how do we make sure that the network is giving us a value from -1 to +1 for the value, like we want? And so the way we do this is by using that hyperbolic tangent activation function. So it's just called tan-h, and it comes from this functional library, but basically what this does, I guess it doesn't have much for documentation here as far as the output, but here is the function that is actually being computed, and this is basically giving you a value from -1 to +1. So we can have f tan-h and just pass our x in there. And this is then the output of our value head. And we should actually really not be calling this x, because remember, we want to pass this same x, we want to separate these heads out. So when we pass this to the policy head, we want our x to still be what it was after our res blocks. So I'm going to change, I'm going to pass x in here, and I'm going to change our x here to v for value. And this last v here is ultimately the value that will be returned by the forward function. So in a similar way with our policy head, I think we can just copy this line. And this will be called P for policy. We'll do the same thing here, except we will use our policy layers. So we have our policy convolution, our policy batch norm. We pass it through our activation function, and then we go straight to, we need to reshape before we get to the policy head. So this will be reshaping to this dimension. We want to add that -1 and reshape to, yeah, so we'll have, in the same way, we'll have 32 by 6 by 7 outputs coming into this next dense layer, which is the policy head. So we can, and again, we need to change this from x to p. So we can add our policy head layer and an activation. And then lastly, we have now our log softmax activation function here, which is actually a layer in the torch libraries. So we need to, what do we call this? Policy ls. So we'll pass p through this log softmax activation function. And now this finally will be the output policy that will be returned by the forward function. So we can go ahead and return VP here for value policy. And again, this V is a number from -1 to 1 that is basically establishing a value from player 1's perspective of the current state of the board, and the policy is a 7-value array, or yeah, a 7-value array of numbers indicating the probabilities between 0 and 1 of choosing a given action. So those 7 numbers will add up to 1. The highest one will be the action we want to take. The reason we use a log softmax here instead has to do with training efficiency. There is also just a regular softmax function, but for some mathematical reason it's more efficient to train with the log softmax function and then actually do an exponential on the end here. So I'm not sure exactly why that is, but I'm sure you can find that documentation online and things. So lastly, I think we can now just basically get a model summary here. So there's a library we can import. Maybe at the bottom we'll just check if, so if we're not, if name equals name, if we're not calling this from some other script, we can basically just print out the model summary, which we obviously don't want to do every time. And I will actually just paste it in here. So this is, I believe I just pulled this from online somewhere and changed some of the inputs to fit our need here. But basically we are just going to call this summary function, which can be imported from, I think it's torch input. Import summary, we'll find out. And basically once I am able to initialize that device, I'll pass it into the model and basically initialize that model. We can use this function, run basically a dummy tensor through it, which is, I use 16 for a batch size here. This could be anything. And then our expected shape. So this is like the shape of our board. And we'll save that here and then just print it out. Actually, I believe I'm out here. Okay, so Python model.py. And there. So you can see the model here. This will give you basically everything you'll need to know about just kind of the structure of the model. It'll show you like how everything is getting passed and what is the shape at each portion and how many trainable parameters are at each stage of the model. So the number of trainable parameters is what will significantly affect your training time and how long like a single epoch of training will take. So in some of these latest models, you'll see this number be on the order of like 100 or 200, I think like 170 billion are some of the biggest ones. So in our case, we only have 612,000 here, which is, you know, quite a lot. And I think we could do actually much more than this, given a decent GPU. So in the rest of the series, we'll probably experiment with what we can get away with here and actually what is even necessary for a Game of Connect 4. I don't think that we will need a huge model to play this game or to understand the state of the board. Basically, what we're kind of trying to balance the trade-off of how many games can we simulate and train on versus the size of the model we need to actually understand the game, right? Because in these Monte Carlo simulations, we actually need to inference the model to run the simulation, and we need to inference it many, many times. So the bigger this number is, the bigger the model is, the longer those simulations are going to take, and the less training is going to get done in any given duration of time. So that's kind of a trade-off that we'll have to kind of balance here and play around with as we decide on hyperparameters to actually tune this model. Yeah, in the next video we will, so on the simulation side, now that we have this model built, we still need to be able to train it and everything, but to be able to train this model, we need training data that will come out of these simulations. So far on the simulation side, we have only been able to simulate just one move through the tree searching process. So now we just need to be able to stitch together that simulation process and actually, you know, inference with the model, get the value and rewards, and simulate a whole game of Connect 4 and pass those to the model for training. So that's what we'll be focusing on, or at least some of that in the next part of the series. So I hope you enjoyed, and I'll see you guys in the next one.